Hello students, welcome to this lecture on linear programming problem. In this lecture, we will cover NCERT section 12.1 to 12.2.2. This is a disclaimer. In today's lecture, first we will discuss NCERT section 12.1 introduction. After that, we discuss core concepts like optimization, objective function, constraints, and then we discuss 12.2 linear programming problem and its mathematical formation. After that, we will discuss 12.2.1 mathematical formulation of the problem. And finally, we discuss 12.2.2 graphical method of solving linear programming problem. I hope you are with your notebooks and pens ready. So now let's get started. First, we will start our lecture by discussing introduction of linear programming problem. So what is linear programming problem? Linear programming problem is a mathematical technique or mathematical tool that helps find the best solution to a problem by using linear equation and inequality. So it finds the maximum or minimum value of a function given certain limits by analyzing the relationships between variables. So this is a method used to find the best solution to a problem where you want to maximize or minimize a goal or objective function while following a certain rules or limits. Okay, the core idea is to use limited resources in the best way possible to reach a goal. Okay, so like making the most profit or spending the least money. Okay, so first we will discuss some key components. So first we will discuss about objective function. So what is objective function? So the objective function is a linear equation like z equals ax plus by, where a and b are constants. Okay, and it represents the quantity we want to maximize or minimize in a linear programming problem. And then we will discuss constraints. So what is constraint? So constraints are limitations expressed as linear inequalities like x plus y is less than equal to 10 or 2x minus y is greater than equal to 3. So they define the feasible region where solution must lie, restricting variable values based on the available resources. So in linear programming, non-negative constants mean variables like x and y must be greater than or equal to 0. That means x is greater than equal to 0 and y is greater than equal to 0. Since they often represent the real world quantities such as items or time. So now let's look at this example. So in this example, it shows a uh, dietitian mixing two foods to meet vitamin requirements. Okay, so the problem provides the minimum vitamin A and C needed in the mixture, 8 units of vitamin A and 10 units of vitamin C. Okay, and the goal is to find the right combination of the two foods that satisfies these vitamin requirements. So first see food 1. So food 1 cost rupees 50 per kg and food 2 cost rupees 70 per kg. Food 1 contains 2 units per kg of vitamin A and 1 unit per kg of vitamin C. Now, let's look at food 2. So, food 2 contains 1 unit per kg of vitamin A and 2 units per kg of vitamin C. So we have to determine the minimum cost of the mixture. So such type of problems which seek to maximize or minimize profit or cost. Okay, from a general class of problems. This type of problems called optimization problems. Okay, so what is the purpose of optimization problems? Purpose of optimization problems are basically maximize or minimize. Okay, maximize profit and minimize cost. Now we see problem solving method. How to formulate an LPP. Okay, LPP means linear programming problems. So now we are going to discuss how to solve how to solve okay linear programming problem or how to formulate an linear programming problem. Okay, so linear programming problem is a mathematical technique used to optimize means maximize or minimize a linear objective function subject to a set of linear constraints. So let's see step 1. Step 1 is to identify decision variables. Okay, so by step 1 we can identify our decision variables in an LPP. When solving a problem, start by reading it carefully to understand what's being asked. Okay, to explain the here assign symbols to these quantities. For example, x, y. So what are x and y? So the symbols like x and y to represent quantities in the table. Okay, so these symbols for example x, y are called decision variables. Okay, now see step 2. Step 2 is to write the objective function which shows what you want to maximize or minimize, like profit or cost. Using the decision variables from step 1, the primary goal is to determine what the main objective is, such as making the most money or spending the least. Okay, to express a goal as a linear function of decision variables, write the goal using only the variables like x and y. Okay, so express the goal as a linear function of the decision variables, for example x and y, and constant with no multiplication between variables. So this linear function is called z. Okay, so z is basically optimal function. Okay, so it is a function that takes inputs and produces outputs in a straight line relationship. Now, let's look at step 3. Step 3 is about finding and writing down all the limits or rules that apply to the problem. Okay, so first identify all the restrictions or limitations mentioned in the problem. So, for each restriction, formulate a linear inequality or equation involving the decision variables x and y. Now, step 4 means you must ensure all variables in your problem are greater than or equal to 0. That means add non negativity constants. Okay, so in linear programming problem, the decision variable must be non negative, meaning they can only take values that are 0 or positive. So, we will take x is greater than equal to 0 and y is also greater than equal to 0. So now let's look at this example. In this example, a dietitian wants to mix two foods to meet vitamin requirements. Food 1 costs 50 per kg and has 2 units of vitamin A and 1 unit of vitamin C. Okay, so food 2 costs rupees 70 per kg and food 2 contains 1 unit vitamin A and 2 units of vitamin C per kg. So the mixture must have at least 8 units of vitamin A and 10 units of vitamin C. Okay, so the goal is to find the minimum cost of the mixture. So let x be the kg of food 1 and y be the kg of the food 2. So now let's start the solution. So this table shows information about two types of food, food 1 and food 2, along with their cost and the amount of two vitamins, vitamin A and vitamin C. Okay, so they provide per kilogram. So food 1 cost 50 rupees per kg and gives 2 units of vitamin A and 1 unit of vitamin C per kg. And food 2 cost rupees 70 per kg and it gives 1 unit of vitamin A and 2 units of vitamin C. Okay, so the minimum required shows that at least 8 units of vitamin A and 10 units of vitamin C are needed. Okay, so now let's see step 1. Step 1, in step 1 we will identify decision variables. Okay, so first let x be the quantity in kg of food 1. This means x represents how much of food 1 is being considered, measured in kilograms. Okay, and let y be the quantity of food 2 in kg. Okay, and this means y represents how many kilograms of food 2 is being considered in the problem. Now, step 2 involves identifying the objective function, which is to minimize cost. Okay, so the cost of food 1 is rupees 50 per kg and food 2 cost rupees 70 per kg. Okay, so total cost z equals 50 times x plus 70 times y. So we need to minimize z. And step 3 is to identify constants. Okay, so constants are vitamin requirements. Okay, so means you must ensure the selected food items meet the minimum or maximum vitamin needs specified in the problem. Okay, so vitamin A contains vitamin 1 has 2 units per kg and food 2 has 1 unit per kg. Okay, so the mixture must have a minimum of 8 units. So this is an inequality. Okay, that we get the mixture needs at least 8 units, that is 2x plus y is greater than equal to 8. Okay, and here look at vitamin C. So food 1 has 1 unit per kg in vitamin C. Okay, and food 2 has 2 units per kg of vitamin C. So now the mixture must include a minimum of 10 units of substance of vitamin C. Okay, so we get this inequality x plus 2y is greater than equal to 10. Okay, so this is an inequality that represents a condition involving two decision variables x and y. Now step 4 for non-negativity constants. So negativity constant means that all decision variables in the problem must be greater than or equal to 0. Okay, so this means that the amounts of food represented by x and y cannot be less than 0. So x and y must be 0 or positive numbers. Okay, so here we get this constants, x is greater than equal to 0 and y is greater than equal to 0. Now the final LPP formulation is the minimize z equals 50x plus 70y subject to 2x plus y is greater than equal to 8 and x plus 2y is greater than equal to 10. Okay, along with x is greater than equal to 0 and y is greater than equal to 0. Now here we formulate this problem mathematically. Okay, so a company wants to manufacture two types of smartphone. model A and model B in such a way that production capacity constraints of 60 hours for assembly and 48 hours for testing per week are met. Okay. So model A generates 200 profit per unit and model B generates 300 profit per unit. Okay. Model A requires 3 hours per unit of assembly time and 2 hours per unit of testing time. Model B requires 2 hours per unit of assembly time and 4 hours per unit of testing time. So we have to determine the maximum profit possible from the production mix. So first of all, think about this. How would you approach this problem? Okay, and then see solution. So let's start the solution step by step. So first of all, look at the following table. Okay, in this table, we have in first column model of smartphone, model A and model B. Okay, and in second column we have profit per unit. Okay, and in third column we have assembly time hours per unit and testing time hours per unit. Okay, so here model A makes a profit of 200 per unit and it takes assembly time 3 hours per unit. Okay, and testing time 2 hours per unit. Model B makes profit 300 per unit and takes 2 hours assembly time and 4 hours testing time. Okay, so here available hours are basically 60 hours and test for assembly time 60 hours and testing time 48 hours. So now we will look at mathematical formulation. So now let's see step 1. So here in step 1 we identify decision variables. So let's see here, let x basically number of model A units. Okay, and let y equals number of model B units. And step 2 involves identifying the objective function, which is this case is to maximize cost. Okay, so model A guarantees 200 profit per unit and model B generates 300 profit per unit. Okay, so the equation z equals 200x plus 300y. Okay, this is actually our objective function that we have to maximize. Step 3 is about constants. So here model A needs 3 hours per unit for assembly while model B needs 2 hours per unit. So maximum assembly time available 60 hours. Okay, so 3x plus 2y is less than equal to 60. Okay, this inequality we obtain. Okay, and model B needs 2 hours per unit of testing time and model B needs 2 hours of testing time for each unit. So now testing time constant is given by the inequality 2x plus 4y is less than equal to 48. Now step 4 for non-negativity constants. Okay, so non-negativity constants basically we make decision variables x and y greater than or equal to 0. Okay, that means x greater than equal to 0 and y is greater than equal to 0. So the final LPP formulation is the maximize of z equals 200 times x plus 300 times y subject to 3x plus 2y is less than equal to 60, 2x plus 4y is less than equal to 48 and x is greater than equal to 0, y is greater than equal to 0. Now we will discuss objective function. So what is objective function? So the objective function is a linear function of two or more variables that we want to optimize, either maximize or minimize. It represents the primary goal of the problem, such as total profit, total cost, or total output. Okay, so now we will see mathematical form. So if x and y are the two decision variables in a problem, then the objective function is represented as z equals ax plus by. Okay, so the equation z equals ax plus by shows that z is a linear combination of x and y, where a and b are constants. So in the linear programming, we aim to optimize z. That means we want to either maximize or minimize. Okay, so z is the value to be optimized, and x, y are the decision variables. A and b are the constants representing the per unit contribution of each variable to the objective. Okay, now let's look at this example. In this example, we are given a profit equation, that is z equals 50x plus 40y, where x and y represent the number of two different products. Okay, and the goal is to find the maximum profit. So in cost minimization, z equals 200x plus 150y, where x and y are quantities of two food types, and 200 and 150 are their unit cost. So now we will discuss constraints. In linear programming, constraints are like rules that limit how we can choose our variables. Okay, they are usually written as linear inequalities or equations, showing what values our variables can take, helping us find the best solution within those limits. So these limitations can be one resources like raw materials, labor, machine hours, or one requirements like minimum nutritional values. So now we will look at mathematical form of constants. So constants are expressed as linear inequalities. So a1x plus b1y is less than equal to c1, less than or equal to type in constancy. This is okay, and a2x plus b2y is greater than equal to c2. This is greater than or equal to type constant. A3x plus b3y equals 3. This is equality type constant. Now we will discuss optimization problem. So an optimization problem seeks to maximize or minimize a linear function that called objective function, subject to a set of linear inequalities. So linear inequalities are called constants. So a complete linear programming problem formulation includes the objective function z, all structural constants, okay, and the non-negative constants, that is the decision variables should be greater than or equal to 0. So let's look at this example. So in this example, we will discuss structure of an LPP. So here we have to maximize z equals 3x plus 2y. Okay, so z equals 3x plus 2y. This is our objective function. So we have to maximize this objective function. And subjective constants are x plus 2y is less than equal to 10, 3x plus y is less than equal to 15, x is greater than equal to 0, and y is greater than equal to 0. Here x and y are the decision variables. Okay, so z is objective function, and x plus 2y is less than equal to 10, 3x plus y is less than equal to 15, x is greater than equal to 0, y is greater than equal. These are our constants. Now we will discuss graphical method. So how to solve a linear programming problem by graphical method, that we will discuss now. So this method is used to solve linear programming problems that have two variables. Okay, and it involves graphic the constants as linear inequality, and we finds the feasible region, which is the common region determined by all constants. Okay, now we will discuss some key terms. Solution: a pair of values x comma y that satisfies all constants of an LPP called solution of the LPP. Okay, and what is feasible region? The feasible region is the area where all the problems constants overlap, including the non-negative conditions. Okay, so here look at this figure. In this figure here it shows feasible solution. Okay, so any point x comma y which lies inside or on the boundary of the feasible region called feasible solution. Now we will discuss infeasible solution. So what is infeasible solution? An infeasible solution is any point x comma y that lies outside the feasible region. Okay, this means the solution does not satisfy all the constants of the problem. So an uh, infeasible problem in linear programming means there is no solution that meets all the given constants at the same time. So the feasible region has no points. Okay, so an LPP is infeasible if its feasible region is empty. So that means there is no point that satisfies all constants simultaneously. Okay, and here in this figure it shows here this area. Okay, this area is called infeasible region. Okay, and this sided region is called basically feasible region. Okay, and here the while the point x comma y lies in this feasible region called feasible solution. Now we discuss optimal solution. Okay, so optimal it also calls feasible solution. So any point in the feasible region that gives the optimal value, either maximum or minimum of the objective function z. So that's all for today's lecture, and thank you for your attention. I hope this lesson was helpful to all of you.